Hey, good morning, everybody. This is Mr. Ainsworth, and we're going to get into a really cool lesson about quadratic functions. Okay, and in this lesson here, dealing with the Empire State Building here, which is a building that I've actually been and visited here, and it's pretty darn tall too, 1,250 feet tall to be exact. Um, we're going to discover here how the rate of change of a quadratic function behaves. So remember, quadratic functions are just these parabolas, these second degree functions that you studied in Algebra 1 and 2. All right, and we are going to explore and go ahead and discover this through this cool lesson. So let's go right into it here. Let's read it and let's go for it. All right, so now penny is dropped from the top of the Empire State Building from a height of 1,250 feet. The height of the penny in feet, t seconds after it's dropped, is given by the function. All right, now check this function out, h of t. It's equal to 1250 minus 16t squared. And notice that the degree of the function is degree 2, and that means you have a quadratic, which is a parabola. And if you remember your Algebra 1 skills, okay, it has a lead coefficient that's negative here, and so this parabola opens down. It's a concave down parabola because the lead coefficient right here is negative. Okay, it's negative 16, and that means the parabola opens down and not up. Not that you have to know that right now, but that's a little trivia. Okay, now it says complete the table to show the height of a penny, okay, the height of a penny at each of the given times, the height above the ground, that is, right? Because it starts at 1,250 feet, all right, and then it goes down and it hits the ground at some point. So let's do it the fast way, okay? So pull up Desmos here. All right, this is your best friend. So press and hold on the Desmos icon, overlap it. All right, simply type the function in, and out pops the values, right? So here we go. So y is equal to, I'm going to do a little variable switch. I'm going to let the range be y and the input be x. Just make it easy on in the Desmos calculator. So you type in your function in terms of y and x. Just do a little variable swap. 16x squared, boom, there it is. Okay, and you won't see that initially. You're going to see something like this. I'm sorry, I have to reset my calculator here. You probably will not see, you'll probably see this right here. So in Desmos, what you're going to have to do is change the scale. And the y-intercept, when t is 0, h of 0 is 1,250. So you got to change the range here. And I'm using my fingers right now because I'm on an iPad and a touch screen. And notice that it starts up there at 1,250 feet, right? And then it's, tossed after, off the top of the building, and it hits the ground. And after some number of seconds, which we're going to find, by the way, it hits the ground. So it says complete the table at each of the time intervals. Like after 2 seconds, how high above the ground is it? After 4 seconds, how high off the ground is it? So let's figure that out. So click on the gear, click on table. All right, this is the easiest way that I could think of doing it. Take out your default values because time can't be negative, and start at 0. And then go enter to enter, and then hit enter a couple times. And you'll have all the values from 0 to 8. And these are the heights above the ground. So let's put these in. So it starts off at 1,250 feet. This is the initial height. Okay, at t equals 0. Remember, these are time values right through here. At 2 seconds, it's 1,186 feet above the ground. At 4 seconds, it's 994 feet above the ground. At 6 seconds, 674 feet above the ground. And then after 8 seconds, it's 226 feet above the ground. Above the ground. So make sure you understand that here. Let's read the problem so you understand what's going on. All right. Now here we go. By the way, you can see as you put the values in here, but watch this. Look at Desmos here. Click on the points and you'll see your heights above the ground. Isn't that cool? And then what you can do, just so that you can screenshot this right here and bring it into your lesson. I like showing you a little bit of technology too while we go through this. So in addition to figuring all the values and everything like that, I like to show you how to use your iPad effectively. Select done, copy and delete, swipe that away, press text mode, and press it and hold on the side of your iPad, and check this out. You now have the graph of the function. right there at your fingertips. Look at that. Isn't that cool? Okay, so there are the values, and it says find the exact time when the penny reaches the ground. Okay, dokie. So the ground is when height equals 0. And again, we're using this function right here. So what we want to do is set the height equal to 0, not the time, but the height, all right, and find out what the time is after how many seconds. And if you look at the graph, look right here. This right here, this point right here is when h equals 0, because it's height here, h here, t here on the x-axis, so the height in feet. On the y-axis, the vertical axis in feet, and this is the time axis, time here in seconds, okay, in seconds. So you interpret the graph here. So notice it's between, let me see, 2, 4, 6, 8, it's between 8 and 10. So, it's some t there, right there, t is between 8 and 10. And the height there is 0. I meant to write that first. Okay, so now what we want to do is we want to figure this out. So let's do a little bit of algebra here. All right, so let's get started. So the function, 1,250 feet minus 16t squared. When is that equal to 0? T equals question mark when that equals 0. When is the height equal to 0? And so when I say h equals 0, I'm talking about h of t equals 0. Find t when h of t equals 0. So you set the function equal to 0, and then you do some algebra here. All right, I'm going to add 16t squared on the other side, so I get 1250 is equal to 16t squared. All right, divide by 16 through here, and then what do I get? I get t squared is equal to whatever 1250 divided by 16 is. Actually, you know what? I'm just going to write it out. 1250 divided by 16, and then of course you got to square root both sides. Put the sound effects in, and what do you get? What do you get? T is approximately equal to whatever this is. Okay, so bring out the calculator again, and then let's figure this out. So type it in. Go to your next line of Desmos. Right here, type in the square root. All right, 1250. All right, you want to divide that by 16 and then read. Okay, and then always round your answers to the nearest thousandths, third decimal place. And the fourth digit's 8, so you round the third digit up to 9. So 8.839. So 8.839 seconds. Okay, round to 3 decimal places. Always in AP. Okay, so what do we? That's what we know so far. So that makes sense because I knew my answer was between 8 and 10, and I got 8.83. So take a look at that. It makes sense. Okay, I'm going to give you a happy face. All right. So then after that, what else do we have to do? Find the average rate of change in the penny's height during the total length of the drop. Okay. Now, don't you notice that we've been using the rate of change in every single lesson? That's why I started off the year with you guys with a review activity on the average rate of change, which we abbreviate AROC, right? Everybody say AROC. Okay, average rate of change. All right, in the penny's height. Okay, so it's the change in height divided by change in time. All right, remember delta means change. The delta, there's a lot of Greek symbols that were used in mathematics, and delta means change. So delta H means a change in height. Delta T means a change in time, obviously. Let me write that a little bit better. Okay, so delta T, there we go. Over the total length of this drop. Okay, well, we know we started off at 1,200 feet, 1,250 feet. So if that's the case, so 1,250 feet, that's the total height, right? Divided by the total time, which we just found to be 8.839 seconds. And then we go ahead and approximate this. So bring your calculator back, and then let's figure this out. Okay, so here we go. So 1250 divided by 8.839. This is not exact, this is approximate because I rounded. Okay, and the average rate of change is 141.4419. Okay, so 141.419 if I keep rounding to the 3 places. Yeah, okay. And then it's feet per second. Okay, feet per second. Always include units. Okay, feet per second. Now, just a little note, because I said that, always include units. Many times at the end of the year when we do our AP exam, they give you 1 point for calculating and 1 point for the units. So grab a red pen and put down always include units. If you do not, you won't get full credit on the AP exam. They're that sticklers, okay? They're very, very, very meticulous, as they say. Okay, number 4. Determine how many feet the penny fell during each 2-second interval, and what do you notice? Okay, so let's do that. And here, each 2-second interval, this is the rate of change. Okay, so we got to find rate of change. So from 1250 to 1186, what is that decrease in height? So let's find out. So all you have to do is subtract. So 1186 minus the previous value, which is 1250. Notice you got negative 64. All right, you always take the second y value, subtract the first y value to get the rate. We know it's decreasing, so your rate of change is negative there. Okay, in fact, it's decreasing each time because obviously it's falling down on the ground. So you know it's a negative rate of change. And then the next one, we got 1250, right? No, excuse me, that's correct. We got 1186. Oh, come on. Second one, 994 minus 1186. That's what I meant to say. So 994 minus, all right, 1186. So you just do your rates of change. Notice this is the rate of change of 192 feet. Okay, and we'll interpret this in a minute here. We'll figure out what these numbers mean here. And then obviously here from 674, so 674 minus 994. All right, so negative 320 feet. And the last rate of change, all right, 226 minus 674. All right, you get negative 448, so negative 448. All right. So it says determine how many feet the penny fell during each 2-second interval. Again, this is plus 2 seconds here, 2 seconds here. These are called 2-second intervals. All right, 2-second intervals. That's your delta t. Delta t is 2. It's constant. All right, and how many feet did the penny fall? So just read carefully right through here. So in the first 2-second interval, it fell 64 feet. So what we want to do is we want to take these rates of change and answer the question. All right, so the penny fell 64 feet in the first 2 seconds. And again, it's negative, so that's why, because it's going down. And then 192 feet in the next 2 seconds, and 320 feet in the next 2 seconds, and then 448 feet in the next 2 seconds. So what is this? It says, what is it telling you? What do you notice? Well, if it's falling a longer distance, okay, in each 2-second period, all right, that should tell you that well, first of all, it's not constant, okay, so the rate of descent, okay, is not constant, and it's going faster and faster and faster, okay? So the rate of change or the rate of descent or the number of feet falling, let me say it anyway, so this is what do you notice here? So the rate of descent, or yeah, you can say the rate of descent, or you can say the number of feet falling. These are feet, okay? So these are feet. So the number, I'll just write it very simply. Number of feet, okay, fallen, all right, is not constant. Okay, it's speeding up. That's the reason why. It is speeding up, all right? It's getting faster and faster and faster until it hits critical speed. Believe it or not, there's a max speed of descent, in the universe. Okay, so number 5 here, complete the table with the average rate of change. Ooh, average rate of change again. Look at this. It's all over this activity. So average rate of change of the height of the penny over each of the intervals. So here we go. So we're going to take delta t, which is 2. We already know delta t is 2. So right up here at the top screen, delta t is 2. And then your delta h is given right here. So this is delta h. All of these are delta h's, change in heights. And we're going to calculate them in each time interval. So our first time interval, And again, I'm going to take these values. So let me grab a color here. We'll just do this one here. We're going to take our first time interval, like this one right here, and we're going to evaluate it. So here we go. Delta in the first time interval, in the first 2 seconds, the rate of change is 64. Okay, so negative 64. It's falling 64 feet in those 2 seconds. So divided by 2, and you get negative 32 feet per second. Okay, feet per second. All right, in the next time interval, you got negative 192 divided by 2. Okay, the delta t's are all the same. They're all 2. All right, and you get negative 96, all right, feet per second. In the next time interval, we get negative 320 divided by 2, which is a negative 160 feet per second. In the last time interval, we got negative 448 divided by 2, and you get negative 224 feet per second. Feet every second. Okay, and these are the average rates of change on each interval. And the question is it speeding up, or is it slowing down or falling at a constant rate? And as I said in number 4 here, because it's falling a longer distance in every 2-second time interval, it's got to be speeding up. Okay, it's getting more and more negative. So you can see that the average rate of change is getting more and more negative. So it must be speeding up. Okay, so the penny, okay, is speeding up. All right, which implies a faster rate. Okay, it's getting more and more negative as you go down. So the rate, its rate is getting more and more negative. It's got to be speeding up, as you can tell here, in every single time interval. And again, how do we know? But because we're looking at the average rate of change. The average rate of change is getting more and more negative. Okay, the average rate of change is getting more negative, which means it's getting faster. Okay, by looking at it. Just look at the values here from negative 32, negative 96, negative 160. So we got negative rates because it's falling down as opposed to going up. Okay, now it says graph the function. All right, so here got to graph the points above here. So 0, 1250. It starts off at the height of the Empire State Building here. So it starts here, right? And then we gotta approximate these values here. So let me zoom out. So let me see, 2, 1186. So go right 2 up 1186. Holy cow, we gotta approximate through here. It's about right there. And then 4, 994. That's almost 1,000, but a little bit less. And then 6, 674. So 6, 674, probably maybe right about here. And then I'm approximating 8, 226. So 8, 226, right about here. And so if you graph the function, check this out. So if you notice that it's getting lower and lower and lower and lower and lower and lower and lower, right? And then it hits the ground right here. Okay, h equals 0 at t equals 8.8. What was it at the top? We counted 8.839. So 8.839 seconds. Okay, and notice this right here. Let's answer the question. Is the graph of h concave down or concave up? And what does this mean in the context of the problem? Okay, well, it's obviously concave down. Okay, CC is concave. Concave, concave. And if you use the down arrow, that means concave down. Okay, it opens downward, guys. Okay, so first of all, it's concave down. But what does that imply in the context of the problem? Well, we talked about in our previous lesson that if the graph is concave down, all right, the rate of change of the penny's height is decreasing. And we should know that if you draw some tangent lines here. I'm just going to draw a few. All right, we have negative slopes on the tangent line, but notice that the tangent lines are all getting steeper. They all have negative slopes, and it's getting steeper and steeper and steeper, more and more negative, right? And if that implies that the rate of change of the penny's height is decreasing. So the rate of change of the penny's height is decreasing. All right, got to think concavity. Okay, and we knew it was going to be concave down because we have a parabola here in the very beginning. Look at this function here. It's got a negative lead coefficient, so I know it's concave down in the beginning, if you remember all your Algebra 1 skills. Okay, now let's see here. We answer all the questions. Oh, by the way, I wanted to do something here. Go back to the initial table. All right, get back here. What's the rate of change of the rate of change? Let's talk about that. Okay, so let's calculate something here. I'm going to just erase a few things just to analyze a few things. All right. So what's the rate of change of the rate of change? What's the rate of change from negative 64? I'm going to switch colors here to negative 192. Okay, what do you subtract from 64 to get to negative 192? So let's bring in the calculator here. The way you get that is by subtracting. Okay, so negative 192, right? Subtract negative 64. And notice it's negative 128, right? So I'm going to write down minus 128, right? Negative 64 minus 128 gives you negative 192. What is the rate of change of the rate of change in a quadratic function? So the numbers in red here are the first rate of change, called the first difference. The second numbers are the rate of change of the rate of change. So let's figure that out. So negative 320 minus a negative 192, right? Negative 128 again. Is the rate of change of the rate of change in a quadratic function always constant? I don't know. Let's figure it out one more time. Negative here, negative 448 minus a negative 320. Holy cow, look at this. Look at that. They were always getting a negative 128. The rate of change of the rate of change is constant. All right, key point right here, guys. Let's highlight it. All right, the rate of change of the rate of change is constant. That right there, my friends, has a special name. So let's write it over here. It's called the second difference. The first rate of change is called the first difference, and the second rate of change of the rate of change is called the second difference. So I can say that the second difference is constant. All right, for all quadratic functions, which are second degree quadratic functions. I'm talking about second degree. So if you take the second difference of a quadratic function, it will always be constant. Okay. Also, just to make the point, all right, because it's always good to make the point. Now watch this. I'm going to do it again with the average rate of change. If we take the rate of change of the average rate of change, is that constant? Well, let's play with numbers and let's figure this out. So right here, what's the rate of change from negative 32 to negative 60 or 96? All right, and you guessed it, it's negative 64. What's the rate of change from negative 96 to negative 160? Well, you guessed it, is negative 64. And if you do the same thing here, from negative 160 to negative 224, that's also a negative 64. So the rate of change of the rate of change is still constant. And that's because we have a quadratic function. So one of the things embedded in this lesson is that the average rate, the rate of change of the rate of change in a quadratic function is constant. And there you go. All right, and then I'm just going to do a few learning targets here, and then you can do your check for understanding. Okay, so what did we just learn in our lesson here? Let's summarize what we've learned, put it all together, and write a few quick notes. Okay, some learning targets, if you will. Okay, so first learning target, LT's learning target, all right, is that the quadratic functions, all right, which are second degree functions, have a second difference that's constant. Okay, so here we go. Quadratic functions. Okay, second degree functions. Okay, like your parabolas that you guys studied a long time ago. Okay, have a constant second difference. Have a constant second difference. Okay, that's the first thing we learned in the lesson right there. Okay, the rate of change of the rate of change, all right, is constant. This is the way you say it, is the rate of change, okay, of the rate of change, all right, is constant. Okay, second thing, second learning target here. So LT number 2. All right, second one, average rate of change, your AROC takes the change in the output, Y, divides it by the change in the input values, which is delta X. So same thing here that you always know. The average rate of change is delta Y divided by delta X. This is your output values, okay, your output, all right, values, your output rate of change, and divided by your input rate of change. Okay, and third learning target and final, let me just make my final note, all right, here. And you've seen this before, but so let's write it down again. So if you have a function that's concave down, like the one that we studied here, okay, this is concave down, abbreviated CC with a downward arrow here. That implies, okay, that the rate of change, all right, is decreasing. Why? Because if you take a look at the tangent lines, the slope of the tangent lines, you start off with a positive slope on the left side. At the very top, you have a slope of 0, and on the right side, you have a negative slope if you pick points along the function. And if you take a look at the rate of change, which is your slope of the tangent line, so your rate of change equal to the slope of the tangent line, just going over concepts from the previous lessons here. All right, if you take a look at that, if you go from positive slope to 0 to negative, it's decreasing. And the opposite of that is increasing, obviously, concave up. So let's draw a picture there. So if you have a graph that looks like it's concave up, it opens up, concave up here, abbreviated CC with an up arrow here. Your slopes go from a negative slope to 0 at the bottom to positive slope here. So that would tell you that the rate of change of the function is increasing. Okay, rate of change of the function of f of x, you can call it f of x or the function, is increasing, okay, over this interval. Okay, so those are the concepts that we applied here in the lesson. And once again, we're just applying some really, really important concepts of concavity, of average rate of change, and taking a look at the rates of change of the rate of change, the first and the second difference, and applying it in this case to a linear function. So now we know, excuse me, a quadratic function. So now we know that through this activity that the rate of change of a quadratics, all right, is constant. Pretty cool. And if you guys are taking physics right now, this should look familiar because they talk about the distance functions, the height functions over time in physics, and you learn how objects fall and what the gravity is and so on. So pretty cool if you're taking physics. All right, now it's your turn. Go through the check for understanding. You could do that on your own, and also check solutions online. And then of course you guys got to do your homework. Okay, and that's right next to it. So give it a shot, and then you have a lot of resources online like look at that, homework solution videos and answer keys and all that. So make sure you check your work online. All right, this is Ainsworth. All right, hopefully that helped you out, and I'll see you in my next lesson.